Hi guys, good afternoon and welcome to this video about calculating the Kc value in our equilibrium topic. During today's class, what I'd like you to do is to listen through to the explanations of the calculations and then pause the video and take them down step by step within your copy. So by the end of this class, you should have 2 examples of the calculation in your copy. Our first calculation reads as follows. The reaction N2 plus 3H2 to give me 2NH3 was allowed to reach equilibrium at 450 degrees in a 1 litre container. It was found that there was 13.6 moles of nitrogen, 1 mole of hydrogen and 1.5 moles of ammonia in the container when the equilibrium had been established. We want to calculate the value of Kc. So we should hopefully recognise this reaction, guys, as our reaction for the Haber process. So when I start my Kc calculations, I always write them out as if I don't know the numbers. So my products go on top, so I have my ammonia and there's a 2 in front of that, so that becomes the power. My reactants go on the bottom, so I have my nitrogen and then I have my hydrogen, but my hydrogen is cubed. And then I fill in the numbers for each of these guys, so I end up having 1.5 moles on the top, all to be squared, all over 13.6 moles where nitrogen should be, and then 1 mole all to be cubed where the hydrogen should be. And popping that into my calculation, or into my calculator even, I get 0.165. Now, an important step to note when you're back up here, if you are not comfortable putting all of that information into the calculator all at once, absolutely do it stepwise. Do your 1.5 squared, write that number down. Then do your 13.6 multiplied by your 1 cubed, and then use your final 2 numbers. You should still get the same answer. Our next question is a little bit longer, but nonetheless still just as easy to participate in. So the first part is asking me to write down my equilibrium constant Kc for the reaction. So again, Kc is products over reactant. We have CH3, COO, C2H5, and we should recognize that from our organic chemistry now, guys, as ethyl ethanoate. And we have water, and we know to make our ester we're going to need a carboxylic acid. In this instance we need ethanoic acid, CH3COOH, and an alcohol. In this case that is our ethanol, C2H5OH. So that's part 1 of our question done. The second part is asking me state how you would experimentally determine the amount of ethanoic acid present in the equilibrium mixture. Well, ethanoic acid is, as it says, an acid, and we know one way to determine the amount of acid in something is to carry out a titration, your favourites. The final part of the question then is asking me to calculate my equilibrium constant Kc. Now if we go back to the reaction and if we go back to our question, you can see that at the very beginning it tells us a few things. We can see that we're given 27 grams of ethanoic acid and 20.7 grams of ethanol. We are also told that we form 9 grams of ethanoic acid. So the first thing hopefully that is springing to mind is that when we're dealing with Kc, we must have moles, because that's what our square brackets mean, not grams. We do not want grams. So the step 1 in this, we're going to have to convert our grams to moles. So I'm going to start with the ethanoic acid, and the number of grams available here is 27 grams. Now we know going from grams to moles, we are going to divide by my relative molecular mass. The relative molecular mass for our ethanoic acid, if we do some rough work, CH3COOH. So carbon is 12, I have 2, so that's 24. I have hydrogen, which is 1, and I have 4 of them, so that's another 4. And then I have oxygen, which is 16, but I have 2 of them to give me 32. When I add all of these together, I get 60. So I take my 27, I'm dividing it by my 60 to give me 0.45 moles. I continue to do the same then for the ethanol and for the ethyl ethanoate. So for ethanol, guys, it is C2H5OH. So again, carbon is 12, I have 2, that's 24. Hydrogen is 1, but I have 5. Sorry, I have 6. So that's an added 6. And then I have my oxygen, which is 16. In this instance, I only have 1, which is 16, and all of that adds up to 46. So I take my mass of ethanol, which is 20.7. I divide it by my relative molecular mass, and I get an answer of 0.45. The last piece of information that the question tells me is that at equilibrium there is 9 grams of ethanoic acid. So again, we're going to calculate our moles from that. We've already calculated our relative molecular mass of ethanoic acid to be 60, so that turns into 0.15 moles. My next step with all of this, guys, would be to write out the equation again. So we would have our CH3COOH plus my ethanol, C2H5OH, to make my ethyl ethanoate, so CH3COO C2H5 plus our water, H2O. So with our equation now rewritten, we're going to write down the concentrations that we do know, and we're going to start by writing down what we initially know. So initially, I know, initially means at the very beginning, I have just calculated that I have 0.45 moles of my ethanoic acid, and I have 0.45 moles of my ethanol. At the very beginning of this reaction, I don't have any of my products, so their concentration is going to be 0. The only other piece of information that it gives me is that at equilibrium, and I've switched the colour now on purpose, at equilibrium I have 0.15 moles of my ethanoic acid. I don't know how many moles of my ethanol or my ethyl ethanoate or my water has been formed. This is where these problems tend to get difficult. We don't know the number of moles of the rest of the substances, but we can figure them out. And the important thing in this is to use our ratio to our advantage. So I'm going to start by looking at my reactants and looking at my ethanoic acid and my ethanol. And hopefully we can all see that there is a 1:1 reaction there. So if at equilibrium I have 0.15 moles of my ethanoic acid, I must also have 0.15 moles of my ethanol according to my balanced equation. Finally, we must figure out how many moles of ethyl ethanoate and water are formed. Since we started with 0.45 moles of my ethanoic acid and we end up with 0.15 at equilibrium, that must mean that 0.03 moles of ethanoic acid have reacted, have been used up. For every mole of ethanoic acid that reacts, 1 mole of my ethyl ethanoate is made. Therefore, 0.3 moles of ethyl ethanoate are formed. Since the number of moles of water is the same as the number of the moles of the ethyl ethanoate formed, the number of moles of water is also 0.3. So just to go over that last step again, guys, identifying that we have used up 0.3 moles of ethanoic acid. Where did I get this figure? Well, I got this figure by taking away my initial value of ethanoic acid and my value at equilibrium. When I took those both away, I got 0.3. Now, because my ratio is 1:1, I know that for every mole of ethanoic acid that reacts, 1 mole of ethyl ethanoate is formed. So if I know that I reacted, or if I used 0.3 moles of ethanoic acid, I must have also created 0.3 moles of ethyl ethanoate and 0.3 moles of water. Now for our final step, we need to ensure that our volume is in 1 litre. If we read through the question again, I can see nowhere in the question that it is any bigger than 1 litre, so we don't have to do anything. What we do need to do now is we need to put these values into our equation for Kc. So Kc is going to end up looking like this. Our value for ethyl ethanoate at equilibrium, 0.3, multiplied by our value for water at equilibrium, 0.3, all divided by my moles of ethanoic acid at equilibrium, which is 0.15, times the moles of my ethanol at equilibrium, which is also 0.15. Again, take your time putting these into the calculator. Go line by line if we're not comfortable with them, but when you work it all out, you should end up with a Kc value of 4. I know these might seem tricky, and I know they might seem a little bit more difficult, but if you do persevere, they will get clearer. The final question that I'm going to expect you to go through today is one where the volume is not 1 litre. So I'm going to go through part 1 and part 2 really quickly and then focus on the value calculation of Kc. So the first question is asking us what is meant by chemical equilibrium, and we know our definition of chemical equilibrium is a state of dynamic balance where the rate of the forward reaction equals the rate of the reverse reaction. It then asks me what effect, if any, on the percentage decomposition, so decomposition means the breakdown of the phosphorus pentachloride for the reaction, if the reaction was carried out at a higher pressure. So we know when a reaction is carried out at higher pressure, it is going to favour the side of the fewer number of molecules. In this reaction, that is the side of the PCl5, the left-hand side. Now be careful with the question. The question is asking us, is this going to affect the decomposition, the breakdown of the phosphorus pentachloride? And the answer is yes, because the equilibrium is being pushed to the left-hand side, not as much phosphorus pentachloride is going to be broken down, so less PCl5 will have dissociated. Finally, we're on to our calculation for Kc. So if we go through our question again, we're going to highlight the important bits. So I can see that a mass of 20.85 grams was heated in a closed 8 litre vessel. That 8 litres is going to become very important. When the reaction had come to equilibrium at that temperature, it was found that 80% of the pentachloride had dissociated. So the first thing I'm going to do is write down what my Kc equation is going to look like. So it's going to have my products over my reactants. Hopefully you will have all noticed as well, guys, that they gave me my first figure in grams. And we know grams is no good to us, so we're going to have to convert that to moles. We know that there is 20.85 grams of our phosphorus pentachloride, and the relative molecular mass of my phosphorus pentachloride, it works out to be 208.5. That's the PCl5. So we take our 20.8 grams, we divide it by the 208.5, and I'm left with the figure of 0.1. At this point now, I'm going to write out my equation and fill in what I know. So PCl5 to give me PCl3 plus Cl2. So I know initially, if I just do a capital I, that I have 0.1 moles of my PCl5, I have no moles of PCl3, and 0 moles of my chlorine. I do, however, know from the question that it was found that 80% of the pentachloride had dissociated, so 80% had been used up. So I need to get 80% of my 0.1 moles. So my 80% is going to multiply by my 0.1 to give me 0.08 moles. Now, what is that figure actually telling me? Well, it's telling me that at equilibrium, I used up these 0.8 moles. So at equilibrium, I'm going to use the E for equilibrium. I have 0.1 minus my 0.08. So I have used up 0.02 of my phosphorus pentachloride. Now, that 0.08, guys, has to go somewhere. It has to go somewhere. And I'm telling you that for every 1 mole of phosphorus pentachloride that is used up, we make 1 mole of phosphorus trichloride and 1 mole of chlorine gas. In this instance, and in this example, we used 0.08 moles of phosphorus pentachloride. Therefore, we must also have used 0.08 of the phosphorus trichloride and 0.08 of the chlorine gas. The final warning step with all of this, guys, and I pointed it out when we were going through the question, is that at equilibrium, we need the vessel to have a 1 litre capacity. But in this question, it had an 8 litre capacity. So what we now need to do is we need to divide our values at equilibrium by 8. So we end up at 1 litre having much smaller numbers. So we have 0.0025 for my phosphorus pentachloride. For my phosphorus trichloride, we have 0.01, and for my chlorine, we also have 0.01. Now, finally, we can add this into our Kc equation. So Kc is equal to PCl3 and my chlorine gas all over my phosphorus pentachloride, PCl5. And now we can substitute our figures in. So Kc is equal to 0.01 multiplied by my 0.01 all over 0.0025. And when I put that into my calculator, I get a value of Kc for 0.04. So guys, thanks so much for tuning in. That brings us to the end of our Kc equations, and you can expect some more next week. Hope you're all safe and well. See you soon.